Start the recording before I forget. Completing the square. So again, if you want, you can think of that as, you know, just the name of a technique, right? Like that whole phrase is describing a thing. Oh, by the way, if you need those for Tuesday, I got some extras up here. Completing the square. So again, the idea is that we want to factor a thing as a perfect square, but it may not be a perfect square to begin with. We're doing this to, you know, get from that sort of standard form that we looked at for a quadratic to the, you know, so-called like vertex form. That's, you know, one reason for doing it, one place that you see it come up, but it's an important enough technique that it has a name, right? So again, the idea is that if I want to complete the square to factor a thing like, let's say y equals x squared plus 8x plus 1. I want to factor that, but I want to factor it as though it's a perfect square. Like I want to force it to look like a perfect square. So the goal is to end up with a thing that looks like this, right? I don't know what goes here yet on the inside and outside, but I know that I want to make it into a perfect square factor with, you know, probably something left over on the outside. So the way that this works, again, is that if we're going to force this to be a perfect square, then what has to happen is that being a perfect square means you got two identical factors, right? So for example, x plus, this marker sucks. X plus 3 maybe squared. That means x plus 3 times itself. And when you expand that, you get x squared plus 3x plus 3x plus 9. And then normally we go ahead and combine those middle terms. Sorry, you guys may not be able to see that all that well, but we normally go ahead and combine those middle terms. But this part, having identical terms here, and that giving you identical terms in the expansion, right? The middle part of that expansion, the outer and inner products, if you want. That's the thing that we lean on to complete the square. Basically, what that's going to tell me is what the factors have to look like. Because I know that if this thing is going to break down, or if I can take this thing and break it down into a perfect square factor, that what has to happen is that this has to break up evenly. So what I do is split that in half. When I say the middle term, I mean the linear one. That doesn't have to be in the middle, but yes, generally is. So plus 4x twice. I'm gonna give myself a little space here. And I'm gonna kind of skip a line. So I always like to do this, you know, kind of like work down and come back up a little bit. What this does is help me see what we're looking at, right? Because these three terms, I basically want to think of these as the first and outer and inner parts of this factored thing that we're looking for, which means the thing that we're missing, right? The completing part means that it's not all there, right? We have to do something to complete the square. The completing part is that we're going to have to sort of bring in or borrow something to use as that last part of the product. So if the first and outer and inner parts of the product are x squared plus 4x plus 4x, what do the factors look like? X plus 4. Right? X squared, outer plus 4x, inner plus 4x, right? The last part would be 16. That's the completing part, is that I need a 16 to be able to factor it like that, right? Now, x plus 4 times x plus 4 gives you x squared plus 4x plus 4x plus 16. The problem right now is that this line, this third line here, is different than all the other ones, right? Because I've added 16 here, right? This is true that these are equal. This is no longer equal to the stuff before it. So we got to adjust for that 16. The way we do that is by either adding 16 to both sides, or since we're kind of working on one side of the equation, add it and subtract it. So this, I'm calling the like completing part, right? That's making it a square. This minus 16, that's, how do you spell adjusting? Adjusting or borrowing. Like I'm borrowing 16 from 1, right? So what's left here is minus 15. And then last thing would be to just, because those are identical, write it as a perfect square. And now we've got this, same thing, same function that we started with, but written as a perfect square. So we have it in that like vertex form, so now I can look at it and read off where it is. Okay, and this is a place there are going to be, a couple of these that we see in this class in the semester that, this is as much about the technique as it is about like the product, like what we get out of it. Like the value of going from this thing to this thing is kind of questionable. Like you can get the vertex from that, and it's not really that much harder than getting it from here. But part of it is about like the process, because there are other places where we're going to need to like force a thing to factor as a perfect square. It comes back up from pre-cal, it comes back up in calculus. So the method is part of the goal here. Okay, questions about how any of that works? All right, so I left you with this one on Thursday. Why don't you guys take a couple of minutes, talk with your group mates about what you came up with. The vertex, the axis of symmetry, the domain and range, you should have those, no problem. So just compare notes, but the completing the square part, see what y'all did, talk about it, see if you agree. All right, so let me give me the vertex. -1, 3. What do we think? Everybody agree? I don't know what it is. How'd you find it, McKinley? Okay, so x is -b over 2a. Okay, so -b is 4, a is 1. So -2. Oh, wait, no, a is 2. Sorry. Just kidding. 2 times 2. So -1. Okay, good. Great. Okay, and then to get the y value, plug that back in, right? Which would be 2 minus 4 minus 16 So negative 18. Right? Okay, where? We did the x value, right? Right? Okay, so then to get the y, just plug that back into the function. So -1 squared is 1, so 2. Plus 4 times -1, so 2 minus 4 minus 16. -2 minus 16, -18. Okay, yeah, so it's -18. Okay, yeah. You can, yeah, you can do it from a graph also. Again, a couple of reasons this is nice is one, like it's fairly quick and straightforward. Two, this one, if you graph it, that is not going to be in like the standard window, right? So if like you graph the thing, you're not going to be able to see the vertex. Now you can manipulate the graph so that you can, depending on what the function is. Sometimes that's easier than others. Like when we get to some application stuff, the vertex, because it's the maximum or minimum or something, that might be off in like the thousands, right? So sometimes messing around with the graph to find it is more trouble than it's worth. Yeah. Okay. Axis of symmetry. X equals -1. Good. Remember, it's a vertical line, so the x equals part is important. Domain and range. Yep, everything, and then the range is, well, what do we need to know? Vertex, which we already have, and up or down. Which way is this thing open? Why? Because the leading term is positive. Leading term positive means it opens up. So this opens up. So is the range going to look like number to infinity or negative infinity to number? Number to infinity, right? It's got a lowest point. The vertex is the floor of this thing. That's the lowest it ever gets. So the range is going to look like, well, whatever that y value is, up. So negative infinity, or sorry, negative, hang on. I'm writing a thing and saying a different thing. -18 to infinity, right? Because it's opening up. Everybody happy with that? Okay. All right. How about the completing the square part? What would be a good place to start here? Factor out the 2. Oops. Everything's even, so let's factor that 2 out. Now we're pretty much just going to work inside that set of parentheses. The 2 doesn't go away. It's just kind of along for the ride. So where I'm going to start again is taking this middle term and breaking it into 2 pieces, 2 equal pieces, plus 1x plus 1x. I'm writing the 1 just kind of for emphasis. So what do the factors look like? If the outer and inner parts of the product are plus 1x. X plus 1, right? X plus 1 for both of them, so that when you multiply it, you get x squared plus 1x plus 1x. So they've got to be x plus 1. What's the missing part then? The last term. Plus 1. So add and subtract 1, right? Or again, if you want to think of that as borrowing it from 8. This one is getting rolled into this stuff that we're factoring. This one is sort of left over on the outside there.
So that becomes -9. And then finally, I'm going to distribute that 2. So 2 times x plus 1 squared minus 18. And then you can see the vertex, -1, -18. I get the +1 is shifting 1 to the left, and -18 is 18 down. The 2 just means that the parabola is going to be a little bit like taller or tighter than x squared would be. Yeah, cool.
Can you just mention the x and y into the HK?
Can you just insert the x and y into the H and K? You can definitely use that as a way to check, but like I said, like at least in part, this is about the method too, not just, you know, getting to the final result. So what I would say is like, do that as a way to check and to help you kind of think about things as you're working through, because the you know, the H, the X value, the vertex, that's going to be what shows up here. That's going to tell you what shows up here, right? Which means it's also going to tell you about what these look like. So it all kind of like fits together, right? So I don't want you to just jump from here to that using that, because, you know, if I say, as I'm likely to do on like a test question, like do this by completing the square, then I actually want to see like working through that too, because there are other places where that's useful. Okay. Everybody else cool with that? All right. Okay. All right, any other questions about that one? Okay. Like I said on Tuesday, the completing the square thing, like it's a technique, it's a whole method. It's a thing that like just seeing me do it twice isn't gonna, you know, suddenly unlock something in your brain. Like you're gonna have to work through it a few times on your own. So, you know, go home, practice with a few in the homework. If you're still having trouble, then come talk to me about it. All right, so we've got all the tools we need. What we're going to do today, or for the rest of today, is look at some problems. So let me just kind of go through these real quick. On the back there, for supposedly a quadratic function f of x has vertex at 3, -1. The function opens down and has the same shape as y equals x squared, meaning that it's not like stretched or shrunk or anything. It's the same, you know, like width. Then write its equation in vertex and standard form. So hopefully you can, you know, kind of think through what that would look like. 5, we've got a function that's modeling the height of a ball in feet as a function of how far downfield it's gone, basically. That one you might want to take a look at the graph. I think you'd be able to kind of get a better sense for what's going on. And then 6 and 7 deal with maximizing an area that you're closing in. So you're building a fence. You want to maximize what's happening. These, I would recommend starting by drawing a diagram. Like draw a picture. That's going to help you kind of frame things and frame. I didn't need to work that in, but it worked out pretty nicely because it's building the fence. Okay, anyway, draw a picture, label stuff, try stuff, try things, right? So the next 15 minutes or so is going to be try and think and talk and, you know, ask questions, and I'll walk around and talk to you and stuff. But okay. Remember, we're talking about functions whose graph looks like this or like this, depending on which way it's opening. So when you see things like minimum or maximum, excuse me, minimum or maximum, that's going to happen at the vertex, right? So all that stuff we talked about on Tuesday about finding the vertex is probably going to be important. All right, I'll let you work. let's talk about the projectile thing. If you graph it, there's what it looks like. And, standard window. This is quadratic and opening which way? Down. Okay, so you got a graph like this that's basically showing you Y values are height, X values are distance, horizontal distance it says. So that's like distance down the field, like how far from the quarterback the ball has traveled. So basically, if we look at this graph, it's like we're standing on the sideline, like watching the path of the ball, right? Pretty much is what we're looking at. And we want to find things like the maximum height, how far the ball had traveled when it reached its maximum height, and then from what height did he throw the ball. All of those should be positive numbers, right? So there's a little bit of a built-in check on if you did things right. Usually, some of the mistakes that you might make there would be, a sign issue. So if you get a negative, something went wrong somewhere. Hopefully it's easy to fix. I would probably want to see a little bit more of this to be able to tell what's really going on. So you can zoom the graph out, or if we don't want to mess with that, again, I know it's a parabola that opens down. What I need to find to get the maximum height is the vertex, right? So if I can find it on the graph, there it is, 30, 24.3 are the coordinates of the vertex. Or I know a lot of y'all did this. You can do the negative b over 2a thing. Now the numbers here are like a little bit messy because we got a bunch of decimal stuff, but you have a calculator, so not that big a deal, right? 1.2, the negatives will cancel. 1.2 divided by 2 times 0.02, apparently that's 30. And then to get the y, plug back in 30. That part, again, a little bit of a drag because of the decimal values and everything, but it's okay. We have calculators, 24.3. How do we answer the question? That's where the vertex is, right? How do we answer the question? Part A. What is the maximum height of the ball? Well, that's not an ordered pair, right? It should just be a number. It's the y value. Yeah, because the function is height as a function of horizontal distance. The maximum height is the y value then. What does 30 tell us? How far the ball traveled. Yeah, that's how far downfield the ball, sort of passes over at its maximum height. We'll see some stuff where we have kind of a similar setup, but it's as a function of time instead of distance. So the x value there would be t. It would be like how long it was in the air before it reached that maximum. But again, really, for the stuff we're looking at right now, anytime you see maximum or minimum, be thinking vertex, right? That's probably what it refers to. From what height did he throw the ball? What are we looking for there? That's the y-intercept, yeah. X is how far downfield from where he threw it, right? That means x equals 0. That's where the quarterback's standing, right? So this point at 0, 6.3, that's point of release. That's ball leaving his hand. So the initial height, and you'll see that also, like I said here, from what height did he throw the ball? We'll also see that phrased as like the initial height, right? Initial just means like beginning. So what happens at the start? 0, 6.3. So we're talking about like, again, like I'm looking from the sideline watching this. Quarterback's standing right here. This is the path of the ball. This would be where it hits the ground. Yeah. And anything that's not in quadrant 1 basically doesn't mean anything for the actual problem, right? The situation. So this would be the y-intercept, which is 6.3. If you don't want to do that from the graph, you could just plug in 0, right? H of 0 equals 6.3. Plugging in 0 is super easy.
because it just makes anything that has an X in it go away, right? So it's just the same thing as that C value.
Okay. Let's talk about this thing with Farmer Ed for a minute. Is everybody okay with all those? Okay, so that's basically just putting names on the different parts of the graph, right? Farmer Ed. All right. Let's just look at number 6 here. Farmer Ed wants to build a fence around his garden. Okay, so I need a garden. Here's the garden, which conveniently sits right next to his barn. I'm gonna draw over all of the, here's the barn. Barn needs doors. Here's the doors. Right, barn doors are white, right? Okay, whatever. There's the barn. Seems really important to draw this well. Okay. He's gonna fence this thing in. Oh, I guess it doesn't make sense for, well, whatever. He's gonna build a fence next to the barn, doesn't need to fence in the side adjacent to the barn, right? So the stuff I'm drawing in blue, that's what he actually needs to build. That's the fence. He has 180 feet of fence. Doesn't need to fence in the stuff next to the barn and wants to build it as big as possible, right? Wants to fence in the maximum amount of area. Okay, a couple of things we can assume. One, he's gonna build it as a rectangle because I don't know, it's weird to fence a garden and not make it a rectangle, I guess. I don't know, whatever. It's a rectangle. Most of the stuff we'll see, it'll be like specified that it's a rectangle. I didn't say that here, but that's what I mean. So he's got to build these 3 sides. If it's a rectangle, what do you know about these 2? They're the same. Okay, so let's call them something. What do you want to label them? X, Y, L, W, whatever. It's called L. If one of those is L, then the other one's L too. Also. The third side, the one that I've got drawn horizontally at the bottom there, it's maybe different, right? It might be the same, it might not be the same, we don't know yet. Call it something else. Okay, so we've got things labeled. What he needs to build to fence this in is an L, a W, and then another L worth of fence, right? Okay, what do we know about how L and W should relate to each other? Nice. 2L plus W equals 180. That's just the perimeter, right? If he's building this and that, he's, presumably going to use up all the fence, right? So 2L plus W equals 180. So that gives me, we call that a constraint. It gives me like some parameters that we're working with it, right? Whatever L and W are, they got to satisfy that equation. What are we trying to do? Find the maximum area. What would the area of this garden he's fenced off be? Length times width, L times W. Okay. So we've got 2 different equations that tell me about what's going on. One of them, again, 2L plus W equals 180. One of them kind of has, some information in it, right? It tells me how they're related. We call that a constraint because whatever L and W are, they got to fit into that. The other one doesn't really say anything, right? A equals L times W. I don't know what A is. I don't know what L is. I don't know what W is. But this is our objective. This is the thing that we're trying to actually do something with, right? So the idea is take this, figure out how to write one of these things in terms of the other one, and substitute it into this. So if I'm going to take that constraint equation, 2L plus W equals 180, this, and solve for either L or W, which one would you like to do? You know, solve that for L or for W? I mean, W is probably easier, right? So W is 180 minus 2L. Well, now I have a way to write W in terms of L. So if I take that and substitute it in here, and then distribute that, and maybe rearrange. What kind of a thing do we have? Area, the thing that we want to maximize, is negative 2L squared plus 180L. What kind of function is that? It's in terms of L instead of X, but like whatever. What kind of function is it though? Quadratic, right? L squared, so it's quadratic. Which way does it open? You got a quadratic that opens down. What are we trying to find? The maximum. You got a quadratic that opens down. Where are you going to look for the maximum? Top, which we call the vertex, in which we have a bunch of convenient ways of finding now, right? All right, so finish that one. We'll pick up there tomorrow. Try the other one too. Again, start by setting up the diagram. The thing that's going to change is basically what the picture looks like, and then what this constraint equation looks like. So see if you can get that set up. We'll pick up there tomorrow. Have a good day.